Hello, everyone. Here is Chapter 6, Normal Probability Distributions. As you can see, there's a couple of sections. Your textbook might be slightly different, but generally the material is still the same. So, review and preview of kind of what we're doing. We're going to talk about continuous random variables, normal distributions, and distributions determined by fixed values of mean and standard deviation. So, we're going to be looking really exclusively at the normal distributions, and particularly we're going to first look at the standard normal distribution. So the standard normal distribution is different than a normal distribution in the fact that it has these criteria to it, that the mean is equal to 0, that means mu is equal to 0, its standard deviation is equal to 1, that is sigma equals 1. You're going to find that in the next section, we'll be able to take the standard normal and the applications that we have and apply it to a normal distribution. But you'll see how we do that here in a little bit. So the skills that we want to develop here is to be able to find the area or probabilities of relative frequencies. So for example, if mu is equal to 0, the area or probability of values lying less than mu, hopefully you think that is 0.5, yeah, because this side would be 0.5 to the left of the mu line right here, and this green area over here would be 0.5 as well. If you sum them together, you'll find that they equal 1. That's kind of the big idea behind basically probability distributions. So a continuous random variable has a uniform distribution if its values are spread evenly over the range of probability values. So this is an example of basically a uniform distribution here on the right. There's voltage, I think, for a car battery. Basically, if you were to take this length here is 2. If you times 2 times 0.5, you'll find that this area equals 1, which shouldn't be a coincidence. Yeah, for basically the requirements for a density curve is that the total area under the curve must equal 1. And that's the same that I was saying right here. The area underneath this curve is going to sum to 1. Yeah, same concept. Every point on the curve must have a vertical height that is 0 or greater. That is, the curve cannot fall below the x-axis. And that's for both the normal distribution and the uniform distribution. Very important because the total area under the density curve is equal to 1. There's a correspondence between area and probability. That's what's so great about it. So, for example, in this one, somebody said, what's the probability that you have a voltage value that's greater than 124.5? What you would do then is you'd figure out the area associated with this. And basically that is this length, which is 0.5. And you have a height of 0.5. You multiply those two together, you get 0.25. Now there's a 25% chance that you have a voltage reading greater than 124.5 volts. The reason why we're using uniform here is I think it's a little easier for you guys to understand that this is area, it's easier to calculate. As you go to a curve like this, you're probably like, how do I calculate that area? What's so great, and if you were looking under the files in our course, I have the standard normal distribution, both positive and negative z-scores printed off for you or scanned in, and you can use those. All right, so standard normal distribution is a normal probability distribution with a mean 0 and a standard deviation of 1. The total area under its density curve is equal to 1, so that means all this area under here is equal to 1. And you'll see now that we're going to have this be a z-score for the standard normal distribution. So a z-score of 0 would mean half the area is to the right of it, and the other half is to the left, which left is this way and right is this way. But finding probabilities when given z-scores. So we'll use the table in your appendix to find these. It's designed only for standard normal distributions, which has a mean of 0 and a standard deviation of 1. It's on 2 pages. One is the negative z-scores, and the other is the positive z-scores. So if we go back, everything to the left of 0 is negative z-scores, and everything to the right is positive. By the way, the table, if you have it up in front of you right now, table A-2, you'll read at the very top, it says cumulative area from the left. Cumulative means summing all the values underneath the area all the way along this curve. So that means basically we're coming from the left. So once we get to 0 here, we have 0.5 to the left and 0.5 to the right. By the way, you might remember what -1 and 1, this area between here, I think you might remember from the empirical rule, but we'll talk about how we can actually calculate those out more directly. Each value of the body table is a cumulative area from the left up to the vertical boundary above a specified z-score. When working with a graph, avoid confusion between z-scores and areas. Z-score is the distance along the horizontal scale of the normal distribution referring to the leftmost column, the top row of the table A-2. The area is the region under the curve referring to the tables in the body of A-2. The part of the z-score denoting hundredths is found across the top of the row. All right, let's go here. This red is basically your z-scores. That's the top row and far left column. This is the negative side, by the way. The right side, you'd have the same exact concepts, except for it'd be positive z-scores. The red, again, is z-score, okay? Probabilities, by the way, will never be greater than 1, and it will always be greater than 0, right? Or greater than or equal to 0, I should say. They'll never be negative. So hopefully that kicks in your mind of like, oh yeah, that's a z-score. That's a z-score, right? I highly recommend that you take a highlighter out and you highlight this column, whatever color you want, and this column right here, the same color. And then up here on this table, highlight that z. And then highlight this box. You know, you don't have to highlight the whole thing, just make a box around it. And then make sure you know that that's this area right here, this blue area. Whoops, let's go back. This area right here. So this is a really helpful slide. I would really make sure you feel good about this one, okay? Areas and probabilities correspond to each other. Z-scores basically is the boundary or the cutoff line, okay? Example 3 here, we have Precision Scientific Instruments Company manufactures thermometers that are supposed to give readings of 0 degrees Celsius at freezing point of water, right? So basically they're dialed in at 0. Tests on a large sample of these instruments reveal that at the freezing point of water, some thermometers give readings above or below 0 degrees, assuming that the mean reading is 0 degrees Celsius and the standard deviation is 1 degree Celsius. Also assume that the readings are normally distributed. Wow, this sounds like it's fitting all the criteria for the standard normal distribution if we wanted to use that. If one thermometer is randomly selected, find the probability that at the freezing point of water, the reading is less than 1.27 degrees Celsius. So I have another video where I show you exactly how you can draw this out in sketches. But right now, I'm just going to talk through it, and you can find that example video and watch that. But basically, you would be looking at your chart, and you would find where basically the probability of, this is your z-score basically, is less than 1.27. So you'd find on the leftmost column, the 1.2, and then on the top row, you're gonna find that 100th place, which is the 0.07, and then you scroll down on your chart, go across and over, and you'd see the 0.8980. And that's the cumulative area from the left. In other words, what's less than that value. Feel free to pause and go back and look at your table. 4 and 5 here. So using that same thermometers in example 3, find the probability of randomly selecting one thermometer that reads above 1.23 degrees Celsius. So in this case, you'd find 1.23 again on your positive z-scores. You'd see 1.2, and then you'd see the 0.03 in the top row. And you'd go to where that is in your table, and I think you'll see 0.8907. But this is asking for the probability that the z-score or x value is greater than 1.23. So we actually need to do 1 minus the 0.8907 to get 0.1093. Make a random selection from the same sample of thermometers from example 3. Find the probability that the chosen thermometer reads at the freezing point of water between negative 2.00 degrees Celsius and 1.50 degrees Celsius. So in other words, you're trying to find the area between these two, or basically the probability between negative 2.00 z-score and positive 1.50. When you want to solve these types of problems, it's best to find the area for the positive, or the right-hand side, the 1.50, and then subtract off the area for the negative 2.0, because that'll leave you with what the middle value is. And if you were to go like a chart like this, you're finding the value up here, and remember it's cumulative from the left, so it's keeping all this area, and then you find the lower bound one. Oops, don't worry, I'll go back. You find the lower value one, and you'd be subtracting off that piece, and then you're just left with the middle. So now I'm gonna go previous. So that's how you can find that 0.9104, okay? So as a check digit for 1.50, by the way, you should find 0.9332. And for a negative 2.0, you should find 0.0228. When you subtract the difference between them, and that's how you get the 0.9104. In other words, about 91% of thermometers will read between negative 2 degrees Celsius and 1.5 degrees Celsius. Finding z-scores from known areas. So procedure for finding a z-score from a known area. So in this case, we know we have an area, or basically a probability of 0.95. In other words, 95% of the data fits there. We want to find the z-score that corresponds to that. Keep in mind, this is an area or probability, which means if we go back, we are looking at the yellow part of the table, the body of the table, and that corresponds to this blue shaded region here, right? So we want to find, like, for example, this right here. This sounds silly, but that corresponds to 0.11%. So in other words, negative 3.05 would correspond to 0.11% left the tail. Well, we want to find 0.95. So if you go to your table and you look at the positive, you're trying to find this z-score that is that cutoff here. And hopefully, if you look at it, you'll see a star or asterisk in your table that says 0.9495 star 0.9505, and that's in the body of the table. And you find the z-score by going to the left and to the top column, and you see 1.645 would be the correct value that we'd be looking for. So that would be the z-score, 1.645. And again, I have a video on YouTube that has more detail on each of these. I'm just trying to summarize here quickly, so that way you can get a vibe on it and then go back and check on these if you need more assistance. Example 7 and 8, using the same thermometers from example 3, find the temperature separating the bottom 2.5% and the top 2.5%. So again, bottom 2.5, all you need to find is where it says 0.025 in your table. So if you go to the negative score, because it's in the bottom 2.5%. So again, one thing you should consider doing here is you should sketch these graphs out, sketch them out, and then shade in what you're looking for. In this case, the bottom 2.5, then you'll be like, oh yeah, it should be a negative z-score, and I think the value should be negative 1.96. Yeah, yep. And then for the positive, or the top 2.5%, hopefully you catch on that this is symmetric, which means that this would correspond to the 0.9750 value on the top 2.5, but it would mean that there is still 2.5% in the top. So you get 1.96 for the bottom and 1.96 for the top. And now, our critical values is z-score on the borderline, separating the z-scores that are likely to occur from those that are unlikely. So this is basically where we're going to start defining basically that unusual, unlikely, whatever value we define as basically being our border or critical value. Finding z alpha in the expression z alpha, let alpha equal 0.025, find the z alpha of 0.025. This is always going to be the right part of the tail, okay? So it's always going to be the positive 1.96 when you find that z alpha. Okay. And that is all of 6.2. So